Signals and Systems Assignment Help. For any help regarding Signals and Systems Assignment Help, visit https://www.matlabassignmentexperts.com/https://www.matlabassignmentexperts.com. Email info@matlabassignmentexperts.com info@matlabassignmentexperts.com or call us at +1 678 648 4277. Problems. P21.1. Consider the following 4 impulse responses. I, H1, T, equals E-U, T, a greater than 0, 2, H2, T, equals E at U, T, a greater than 0, 3, H3, T, equals E at U, T, a less than 0, 4, H4, T, equals E at U, T, a less than 0. A. Verify that with an ROC corresponding to Re, S, A. B. It is easily verified that in all 4 cases the system functions, i.e., the Laplace transforms of the impulse responses, have the same algebraic expression. However, the ROC is different. For each of the 4 systems, identify which of the S-plane diagrams in figures P21.1-1 to P21.1-6 correctly represents the associated Laplace transform, including the ROC. Also indicate which diagrams correspond to stable systems. P21.2. Consider the LTI system with input xt equals EU, t, and impulse response h, t equals. A. Determine xs and hs. B. Using the convolution property of the Laplace transform, determine ys, the Laplace transform of the output, y, t. C. From your answer to part B, find y, t. P21.3. As indicated in section 9.5 of the text, many of the properties of the Laplace transform and their derivation are analogous to corresponding properties of the Fourier transform developed in chapter 4 of the text. In this problem, you are asked to outline the derivation for some of the Laplace transform properties in section 9.5 of the text. By paralleling the derivation for the corresponding property for the Fourier transform in chapter 4 of the text, derive each of the following Laplace transform properties. Your derivation must include a consideration of the ROC. A. Time-shifting property, section 9.5.2, B. Convolution property, section 9.5.5. P21.4. Consider a continuous time LTI system for which the input xt and output y, t, are related by the differential equation. Let xs and ys denote the Laplace transforms of xt and y, t, and let hs denote the Laplace transform of the impulse response h, t, of the preceding system. A. Determine hs. Sketch the pole zero plot. B. Sketch the ROC for each of the following cases. I. The system is stable. 2. The system is causal. 3. The system is neither stable nor causal. C. Determine h, t, when the system is causal. P21.5. Consider the following system function hs and its corresponding pole zero plot in figure P21.5. Using the graphical method discussed in the lecture, find IH, O, 4H, O, IH, JL, 1. 4H, JL, H, Ju, and 4H, Ju. Sketch the functions IH, JW, I, and 4H, JW. P21.6. For the following system function, plot the pole zero diagram and graphically. Determine the approximate locations of the peaks and valleys of IH, JW, 1. Optional problems. P21.7, A. Draw the block diagram for the following second-order system in terms of integrators, coefficient multipliers, and adders. B. Sketch the pole zero plot of HS and plot IH, JW, under the following conditions. I, W, IS kept constant, but R is varied from close to 0 to close to 1. 2. R is kept constant, but W is varied from about 0 to infinity. You don't have to be precise, but show how the bandwidth and location of the peak changes for the two cases above. A. Consider the following system function HS. Draw the block diagram for HS implemented as I. A parallel combination of second-order systems. 2. A cascade combination of second-order systems. B. S implementation. 2. Unique. P21.9. Complete the Laplace transform pairs given in table P21.9. You may use the following transform of EO, T, as well as general properties of Laplace transforms to derive your answer. You may also use earlier entries in the table to help you derive later results. P.21.10. Figures P21.10-1, P21.10-2, and P21.10-3 contain impulse responses H, T, frequency responses H, JW, and pole zero plots, respectively. A. For each H, T, find the best matching IH, JW. B. For each H, JW, find the best matching pole zero plot of HS. Consider entries with references to other plots, such as 3 and 5, or B and H as a pair. Solutions. Following our previous arguments, we can integrate only if the function dies out as t goes to minus infinity. E' will die out as t goes to minus infinity only if re x is negative. Thus we need re a plus s 0 or res a. For s in this range, b, I, high, t has a pole at a and no zeros. Furthermore, since a greater than 0, the pole must be in the left half plane. Since high, t, is causal, the ROC must be to the right of the rightmost pole, as given in D, figure P21.1-4. 2. H2, t, is left-sided, hence the ROC is to the left of the leftmost pole. Since A is positive, the pole is in the left half plane, as shown in A, figure P21.1-1. 3. H3, t, is right-sided and has a pole in the right half plane, as given in E, figure P21.1-5. 4. H4, t, is left-sided and has a pole in the right half plane, as shown in C, figure P21.1-3. For a signal to be stable, its ROC must include the FW axis. Thus, C, D, and F qualify. B is an ROC that includes a pole, which is impossible, hence it corresponds to no signal. S21.2, A, by definition. If the real part of 1 plus S is positive, i.e., res 1, then thus the condition on re to S is the ROC and basically indicates the region for which 1 plus S is equal to the integral defined originally. Similarly, B, by the convolution property of the Laplace transform, Ys equals H S x S in a manner similar to the property of the Fourier transform. Thus, where the ROC is the intersection of individual ROCs. C, here we can use partial fractions.